right. Thanks for having me. I'll be talking to you about what could be called projective codes in projective spaces. You could also think of it as packing points in projective spaces. But before I get into the math, I want to show you an application of these things so you can understand why we might care about these objects. So this is a graph that describes how movie theaters are doing. And actually, this is how they were doing before COVID-19 hit. So the key thing I want to point out is that this line graph is on the decline, and that's billions of tickets sold. The bars represent revenue, and that was increasing because they were doing some gimmicks of sorts, like really expensive tickets so that you can have a big cushy chair that reclines, and maybe you're buying alcohol while you watch the movie, this sort of thing. But the interesting thing is this line graph going down. For whatever reason, folks aren't going to the movies anymore. Again, this is before COVID-19, so these days it's much further lower. But even when we bounce back from this pandemic, there's going to be this issue of getting people to come to the theater. And you could explain this based on better home theaters, but the bigger problem is easy access online. And I'm not talking about access through Netflix or what have you. I'm talking about the kind of access that maybe you shouldn't have, the access that comes from media piracy. So it's not too difficult to find movies that you might want to see that are available in the dark parts of the internet. And maybe they'll have something like a watermark that indicates that, hey, maybe this was obtained illegally. What frequently happens is movies are distributed to reviewers to decide who should get awards, and then maybe there's a recipient of a DVD or a file who slips it onto the internet or something, and so you end up with this watermark. If you want to make the movie look legit, you might crop out this watermark so it doesn't reveal that there was a watermark there. What would be better is a personalized watermark, so that if the watermark is still on there, you can identify who the culprit is. What would be even better is if there were a fingerprint that's not detectable by the human eye. So nothing so overt as this text, but maybe some noise that maybe correlates with the imagery, something like this. So I want to point you to this concept of fingerprints. The idea is you have a signal, like this is the movie file, and then you have some secret fingerprints that are personalized, phi1 through phi n. And when you give a copy of the movie to each person, what you actually give to them is the movie plus this personalized fingerprint. Now, none of the recipients knows what the true movie is, and they also don't know what their personalized fingerprint is. So they don't have an obvious way of removing the fingerprint. And so if one person decides to put his fingerprinted copy on the internet, then you'll be able to see, just subtract the movie off of the sum, and it'll isolate the fingerprint, and you know who the culprit is. But culprits are smarter than that. What they'll do is they'll collude with other culprits, and so maybe these orange culprits are the bad guys. They're going to try to make it super difficult for you to identify who they are. So they're actually going to make a mixture of their fingerprinted versions. They're going to take some sort of convex sum of their fingerprints. And what that'll do is, I mean, the convex sum of these things will just be the pure movie plus a convex sum of fingerprints. And maybe they'll add noise on top of that to cover their tracks. So let's say that this version, this forgery, ends up becoming popular on the internet. Then what I can do as the person who owns the movie, what I can do is I can take that forgery and subtract off the movie, and then that isolates this noisy linear combination of fingerprints. I can identify the fingerprint that looks the most like that combination, and I'll interrogate the person corresponding to that fingerprint. I would only be interrogating one person, but I could let the legal process take its course, and maybe we'll find the other culprits. The theorem here is that if the fingerprints look different from each other in a certain way, and there aren't too many culprits, and they don't add too much noise, then it turns out that this person we interrogate is likely to be a culprit. The false positive is unlikely. So what we're going to be interested in is designing fingerprints, unit vectors for which the modulus of pairwise inner products is small. We're going to try to design these fingerprints. And that's the whole point of this talk. But I want to zoom out and give you like a bigger picture for what this sort of problem is all about. What we're looking at is we're looking for unit vectors. And here our unit vectors are either going to be in RD or CD. So the field could be real or complex. And we want to select these vectors in a way that minimizes what we call coherence. So this is the maximum absolute value of pairwise inner products. We're going to call it mu, okay? Mu for coherence. So another way to describe this is in terms of vectors, but you can also think of this in terms of the lines that these vectors span. These lines can be viewed as points in projective space. What we're looking for are endpoints in projective space that maximize the minimum pairwise distance. So we're trying to scoot these points in projective space to be as far apart from each other as possible. And I told you why one might care about this in the context of digital fingerprinting, but there's a bunch of other applications of these things. In the case where the field is complex and d = 2, it turns out that the projective space is identical to the 2-sphere. And so packing points in this 2-sphere amounts to what's known as the Thomas problem. Back in the 1930s, there was this Dutch botanist named Thomas who looked in his microscope at a pollen grain and noticed that these long dangly things called pores were very far separated from each other. And so he posed the mathematical problem of how do you arrange points on the sphere so that the minimum pairwise distance is as large as possible. And ever since he posed that problem, mathematicians have been trying to solve it ever since. The problem that we're discussing in this talk is a general version of the Thomas problem. We're not restricted to CP1, but we're certainly interested in CP1, for example. In order to solve this packing problem, there's really two things you have to think about. One thing is you want a good lower bound on coherence. You want to be able to say that it's impossible for the coherence to be smaller than a certain number. And there are a few different techniques for finding such a lower bound, and I list these here. We're actually going to go over all of these. But once you have a lower bound, you're going to try to find a packing that achieves equality in that lower bound. Once you achieve equality in the lower bound, you know that, well, my coherence equals the coherence that is less than or equal to all other coherences. So I must have optimal coherence. And the way we construct packings that meet lower bounds is, well, we'll use representation theory. We'll try to spin up a vector using a representation to obtain a highly symmetric collection of lines, say. We might also borrow techniques from combinatorial design theory to arrange vectors in an intelligent way. And otherwise, we have to just see how we can do with optimization, and minimizing coherence amounts to a highly non-convex optimization problem. So this could be a frustrating enterprise, actually, is this optimization problem here. I wanted to give you a concept of what this problem is like. So I wanted to walk you through low-dimensional examples of this problem, things we can actually visualize. So we'll start with lines in R2. So this is RP1. The optimal arrangement of lines, of two lines, is like the X and Y axes together. If I want to arrange three lines, then I pass them through diagonals of a hexagon. And really, these examples are probably what you would expect. It's not too difficult to see that RP1 is the same thing as the circle as a metric space. And so arranging lines in the plane is identical to arranging points in the circle. And the best way to arrange points in the circle is by having them be equally spaced. This can be phrased as a pigeonhole argument. So the case of lines in R2, pretty straightforward. The case of lines in R3, however, really starts to capture the complexity of this problem. So I wanted to show you what optimal packings look like in this setting. So these are three-dimensional shapes. They're polyhedra. And I want you, at the moment, they're not lines, but there's a way to interpret these objects in terms of lines. For each polyhedron, consider the vertices, and notice that there's actually two n vertices. So in this case, I have 6 vertices. In that case, I have 8 vertices. And you can pair up these vertices in antipodal pairs. And each of those pairs will determine a line. And it turns out that all of these lines intersect at a common point that we'll call the origin. So those lines through the origin are the optimal arrangements of lines. And in fact, they're uniquely optimal in each of these cases. So in this case, the 3 lines you get are essentially the x-axis, y-axis, and z-axes. In this case, you get an arrangement of points or an arrangement of lines that one might call the simplex. They come from antipodal points in the cube. This shape right here is the icosahedron. So if you play Dungeons and Dragons, you might call this D20. And there are other shapes. We are going to describe all of the math necessary to show that these shapes give you optimal line packings. That's one thing we'll cover in this talk. But I want to point out that each of these examples, most of these examples uses a completely different proof. So And in fact, this example right here was an open problem until recently. And the case where n equals 9 is an open problem. So we know a lot less than we don't know in this setting, which is frustrating, but it's also interesting. It means there's lots of math to do. So, okay. I want to start by showing you a class of results that makes up the bulk of what we understand about this problem. Okay, so it revolves around this thing called the Welch bound. So let's talk about the Welch bound. So I have n lines or n vectors in d dimensions, either real or complex, it doesn't matter. If you have that many vectors, then the coherence is necessarily greater than or equal to this square root, okay? The square root of n minus d over d by n minus 1. So this seems like a oddly specific number, but the proof is extremely straightforward. In fact, it fits in this line right here. I won't bore you with all the details, but you stack your vectors as columns of a matrix. You might call it the matrix representation of your system of lines. And then you take a matrix norm, you observe it needs to be non-negative, then you rearrange in terms of the Gram matrix of your line system, and then you note that you can bound the off-diagonal entries of your Gram matrix in terms of the coherence. If you rearrange this inequality by isolating mu, the coherence, you get the Welch bound. The proof reveals when you can achieve equality in this Welch bound. And remember, if you achieve equality in a lower bound of the coherence, it means that you have minimal coherence, so you're an optimal packing of lines. So for this inequality to become equals, I need my Gram matrix to have all off-diagonal entries of equal modulus. And we say that a system of lines of that form is equiangular. Every pair of lines has the same interior angle. In order to achieve equality for this inequality, I need 5 phi star to equal this multiple of the identity. This is less obvious what this is saying. It's called a tight frame, and I wanted to give you a picture to illustrate how tight frames are actually natural. In fact, they're a natural generalization of the notion of an orthonormal basis. You'll recall that an orthonormal basis gives you something of a Pythagorean theorem for any vector in the vector space. If you look at his projection onto the line spanned by each of the vectors, the norm squared of the original vector is going to equal the norm squareds of the projections. And that's the Pythagorean theorem in so many words. A tight frame is allowed to have more vectors than the dimension of the space. So here are 3 vectors that form a tight frame. And it turns out that if you project onto each of the lines spanned by these vectors, and you take the sum of the squares, then it's almost the norm squared of the original vector. You just have to multiply by a correction factor. In this case, the correction factor comes from the fact that we have 3 vectors in our tight frame over a 2-dimensional space. There are a few reasons to care about tight frames. They've been an object of investigation in their own right. They offer a painless reconstruction formula for these sorts of least squares problems. And in the context of lattices, they are known as eutactic stars. Okay, so I introduced the Welch bound. This is a lower bound on coherence. I also gave you a characterization of equality in the Welch bound, these so-called equiangular tight frames. So this suggests that we can find optimal line packings by hunting for this special class of optimal line packings called equiangular tight frames. And this is what the bulk of the research in this world has focused on. I wanted to give you a broad overview of what this line of inquiry has looked like. There are two flavors of results, one in the real case and one in the complex case. And I wanted to drill down the fact that the real case you should think of as easy given the current literature. Everything factors through this notion of a strongly regular graph. So I'll remind you that a strongly regular graph is a graph where every vertex has the same number of neighbors. If two vertices are adjacent, they have lambda neighbors in common. And if they're not adjacent, they have mu neighbors in common. So in the case of the 5 cycle, each vertex has 2 neighbors, so k equals 2. If you're adjacent, you don't have any neighbors in common, so lambda equals 0. And if you're not adjacent, you have 1 common neighbor, so mu equals 1. So it turns out that every real equiangular tight frame comes from a strongly regular graph. So the icosahedron comes from an equiangular tight frame of 6 vectors in R3. And that corresponds to the fact that the icosahedron has 12 vertices. So you think of the ETF vectors and their negatives as forming vertices of the icosahedron, and you can split up the vertices of the icosahedron into 4 classes. You isolate a vertex, that's one class. His neighbors form another class, and then you go to his antipode and his neighbors, and that covers all of the vertices. And you'll notice that the neighbors of the original point form a pentagon. It's in this way that the equiangular tight frame corresponding to the icosahedron corresponds to a strongly regular graph, in this case, the pentagon. In general, you can identify the strongly regular graph from the Graham matrix by isolating any vector you want and then normalizing the other vectors to have positive inner product with that first vector. And then the sign pattern of the Graham matrix between those other vectors will end up determining a strongly regular graph. So you can construct all known real equiangular tight frames by thumbing through Brouwer's table of strongly regular graphs online. There's an explicit subset of those strongly regular graphs correspond to real ETFs in this way. And so you can just build the ETF from its Graham matrix using those strongly regular graphs. So I say it's easy just by pulling from what's known about strongly regular graphs. There's an interesting arrow in the other direction where people have built new equiangular tight frames, and that has produced new entries in Brouwer's table. This is what happened with Tremaine ETFs, for example. Okay, so the real case is easy in the sense of existence. It's also easy in the sense of non-existence. We have really good non-existence results coming from a lemma that I think every math instructor should know. Every math instructor should know this lemma because it's super useful for coming up with homework problems in linear algebra. So this is where you should pay attention. So if you have a symmetric matrix with all integer entries, and the eigenvalues of this matrix have distinct multiplicities, then it turns out that the eigenvalues of your matrix are necessarily integers. Okay, so this is useful for coming up with linear algebra problems because you want the answers to come out as integers. So that's the reason there. In the context of real equiangular tight frames, we can we can establish that certain things that have no business being integers, we can say that they must be an integer in order for an ETF to exist. So here's the Gram matrix of our ETF. Since our ETF is a tight frame, it necessarily holds that the Gram matrix is a multiple of an orthogonal projection matrix. In fact, it's n over d times an orthogonal projection matrix. So the spectrum has to be zeros and n over d's. That's coming from this side of the equality. The Gram matrix is an identity matrix plus mu times a matrix of all integers. S is a matrix with zeros on the diagonal and plus minus ones on the off diagonal. So thanks to this lemma, we know that S is going to have all integer eigenvalues. And so if I read off identity plus mu S, the eigenvalues, namely 0 and n over d, have to be in this strange set of numbers. It has to be 1 plus mu times the integers. So if you unwrap all of that logic, you're only going to have a real equiangular tight frame if both of these square roots happen to be integers. These are square roots of rational numbers, and somehow those have to be integers. So these are extremely strong conditions on numbers of vectors and dimension of the space for a real equiangular tight frame to exist. But it's not so strong that these are sufficient conditions. It was recently shown that there are no 76 vectors in R19, even though d equals 19 and n equals 76 satisfies these integrality conditions. So the real case is easy, both from the perspective of existence, thanks to strongly regular graphs, and in the sense of non-existence, thanks to these integrality conditions. This is the opposite of true in the complex case. In the complex case, you should think of it as hard. It's hard establishing existence. There's no analog to strongly regular graphs. The reason being that the Gram matrix of our vectors are no longer given by a certain sign pattern. We now have these complex phases. So instead of having plus minus 1 being signaling some sort of combinatorial structure, we have these phases that it's difficult to establish what sorts of structure it's begging for. So the research program has been to just throw whatever you can at the problem and see what sticks. So one natural thing is to say, well, I want my lines to exhibit symmetry because symmetry feels optimal. So maybe I'll generate a system of lines using some representation theory. I'll just have a group acting on a line and seeing what sort of ensemble is spun up. And if you look at a particular type of representation, then you can establish what sorts of lines it takes to spin up an equiangular tight frame, and that's given one type of family of constructions. There are a bunch of other techniques. You can try to put together an equiangular tight frame by hand in a small example, and then generalize that construction to an infinite family. That's been successful. You could take examples that we have from the strongly regular graph literature in the real case, and you can figure out how can I generalize these examples in order to produce complex analogs. So we've had success doing that. These examples from group actions, they're inherently algebraic. You can relax the algebraic structure to identify the underlying combinatorial structure that is actually calling the shots, and that will produce even larger families of equiangular tight frames. We have no idea how close we are to completely exhausting the list of equiangular tight frames because there's no non-existence results. We don't have an analog to integrality conditions. There's my colleague Matt Fickus posed a conjecture where he's willing to give you $100 or $200 depending on whether you prove or disprove this thing. He conjectures that you're going to have a vector, an ETF of n vectors in CD only if one of these three numbers divides the product of the other two. You'll notice that these are the numbers that show up in the Welch bound. So there's all of the data we have to date suggests that this conjecture is true. We have an example, the only case where we know ETFs don't exist, the only non-obvious case, is where you have 8 vectors in 3 dimensions. And this required a lot of computation to find a Grosvenor basis for the defining polynomials. It took about a day of computation to show that there are no solutions in this setting. So, okay, complex case is hard, enough said. I wanted to give you a taste for how one might construct an ETF in the complex case. And this is an example that uses symmetry, so it's particularly pleasant. This actually produces a lot of examples of equiangular type frames. So here I have the numbers 0 through 6. I want you to think of that as a cyclic group. And I take the indicator function of the set 1, 2, 4. Okay. If you take the Fourier, the discrete Fourier transform of this indicator function and take the modulus squared, what you get is a spike at 0. The height of the spike equals 3 because there's a contribution of 3. And then all of the other entries are equal to each other. Okay, so this spike plus constant behavior is really coming from the fact that D is something known as a difference set. So if you take the table of all differences between members of D, then you end up like 1, I guess 1 minus 1 is 0, 2 minus 1 is 3, 4 minus, nope, I said it wrong. 2 minus 1 is 1, 4 minus 1 is 3, etc. Okay, so on the diagonal, you're going to get all zeros because that's when you're subtracting a number by itself. On the off diagonal, we end up covering all of the non-zero members of Z7 same number of times. So if you were to take the histogram of differences, you'd end up with a spike plus flat behavior. The fact that the modulus square of the Fourier transform is also spike plus flat is a consequence of the convolution theorem in Fourier analysis. How is this related to lines, you might ask? Well, this difference set gives you instructions for how to design a representation of Z mod 7. So in particular, take the diagonal matrix of, what is omega? It's a primitive 7th root of unity. So take omega to the 1, omega to the 2, and omega to the 4 as diagonal entries of a diagonal matrix, call it H. And the powers of H form a representation of Z mod 7. And if you use those matrices to spin up the all ones vector, then you'll get an equiangular tight frame where the inner product between 2 members of the orbit equal the Fourier transform of this indicator function at the difference of those 2 exponents. So this spike plus flat behavior ends up corresponding to the sort of Gram matrix behavior we would hope for in an equiangular tight frame. Okay, that's enough about equiangular tight frames. We really dug into the Welch bound. I want to show you what we can do beyond the Welch bound, beyond these equiangular tight frames. So in order to do that, I'm going to show you another way to prove the Welch bound, okay? So before we go beyond the Welch bound, we're going to do a little bit more Welch bound. So this is a cool move. It turns out you can prove the Welch bound by taking projective space and embedding it into a higher dimensional sphere, okay? So the way you do this is you take a unit vector representative of your line, and then you pass it to the outer product of that vector times his conjugate squared, or conjugate transpose. And then you subtract off enough of the identity to make this thing have 0 trace. So this forces it into a hyperplane in operator space. And in fact, if you look at what the norm is, you're going to get the square root of 1 minus 1 over d. All that to say, these are points that are residing in a sphere in higher dimensional space. So somehow we managed to embed this projective space into the sphere. If you apply this to vectors in R2, you'll get the identification of projective space with the circle. Once you, oh, and this is an isometric embedding. So you're looking at distances between points in the embedded sphere. That's going to correspond to distance between points in projective space. The cool thing is we have a lot of technology already from spherical codes in identifying what does it take for a collection of points in the sphere to be optimally spread out to maximize the minimum distance. If you don't have too many points, then the optimal configuration are the vertices of a simplex that reside in a subspace. This is known as Rankin simplex bound, and if you want to open up all of the notation, this is how you write it. But the big idea, the broad strokes, is that you take your system of lines, you embed it as a system of points in the sphere, and then you observe that this collection of points in the sphere must satisfy Rankin's simplex bound. So if you pull back Rankin's bound to projective space, it turns out that you recover the Welch bound. So this is another way to prove the Welch bound. But this this proof technique for lower bounds has legs. There are other bounds you can apply in the spherical case and then pull back to the projective case. For example, you can take Rankin's orthoplex bound. This says that if you have enough points in the sphere, then the optimal configuration is obtained by taking vertices of the orthoplex or a subset thereof. So for example, if I take my 4 lines, my optimally packed lines in R2, and I lift up to the circle, I end up with these 4 equally spaced points. These are points that make up the vertices of the orthoplex in R2, namely the square. If you pull back Rankin's orthoplex bound, you get this lower bound on coherence. The coherence has to be at least 1 over root d, provided you have enough vectors. You can achieve equality in this using construction known as mutually unbiased bases. These are collections of vectors that are particularly relevant in the context of quantum information theory. You can generalize this lifting trick. Take a function for which there exists a lifting, where the inner product between the lifted vectors ends up being this function of the modulus squared of your original vectors. This is a generalization of the phi star minus 1 over d identity trick. It turns out you can optimize over the set of zonal kernels, over the set of functions for which there exists a lifting. And by identifying any zonal kernel that satisfies these constraints, you end up getting a lower bound on the optimal coherence. You can optimize Fs that satisfy these constraints using linear programming, and this ends up delivering Delsart's linear programming bounds, a special case of which is the Levenstein bound for when you restrict to polynomials of degree 2. The big picture is captured in this graphic. So this lists all of the best known packings in R6. So lines in R6. The black dots are the best known coherences for packings. These are made available by Neil Sloan on his website. The curves give you the lower bounds that we discussed. We have the Welch bound. You see that the Welch bound gets equality when I have 7 lines in R6 or 16 lines in R6. the orthoplex bound takes over right after 21. So not at 21, but just after 21. So like 22, etc. The orthoplex bound takes over. It turns out there are 22 vectors in R6 that achieve equality in the orthoplex bound. And then after that, Levenshtein's bound takes over, and you see there are 36 lines in R6 that achieve equality in Levenshtein's bound. Okay, so you might think, wow, all of these dots are really close to the lower bounds, and that's right. In fact, you can prove a theorem that says in this regime where the Welch bound is dominant, all of the black dots are within a constant factor of the Welch bound, not just for not just for 6 dimensions, but in general, that's going to hold true. And then you might wonder, how can I close the gap between these curves and the black dots? Like you see a considerable jump here, for example. How do we close that sort of gap? So there are generalizations of these zonal kernel methods I described. This allows you to do more extensive semi-definite programming in order to help to close these gaps. But unfortunately, it appears that those methods don't give you any tight lower bounds. If you want a tight lower bound, you can start flexing more serious algebraic geometry. Tarski-Seidenberg projection gives you a tight lower bound, but it ends up being rather slow. I do want to say some words in that direction. So this is actually a pretty neat thing. The set of Gram matrices consists of rank D matrices. The diagonal is going to be all ones, and it's going to be positive semi-definite. I want you to also consider all possible x's for which the square of the coherence of G is less than or equal to x. So we're looking at all possible ordered pairs of Gram matrices and upper bounds on the square coherence of G. This is a semi-algebraic set. And if you were to take this semi-algebraic set, right, it's a subset of matrix space, comma, real numbers. If you were to take that set and project onto the second coordinate, onto the real numbers, what you'd get is an interval. And it's the interval of all possible x for which there existed G, such that the coherence squared is at most x. So if you were to minimize x after projection, that would give you the optimal coherence. The cool thing is we understand what the form of this projection ought to be. This is the content of the Tarski-Seidenberg theorem, which is to say that the projection of every semi-algebraic set is semi-algebraic. This is interesting because we're frequently interested in projecting algebraic sets. And so you might hope that the projection of an algebraic set is algebraic. It's not. It's only guaranteed to be semi-algebraic. For example, you project the circle onto the horizontal axis, you end up with an interval. That's not an algebraic set, but it is semi-algebraic. So this gives us a method for finding the optimal coherence. We just have to figure out what this interval is. And then the left-hand endpoint of the interval is the minimum possible coherence. This can be accomplished by running cylindrical algebraic decomposition, which is available in Mathematica, but the runtime is double exponential in the number of variables. So it's going to take a long time in order to try to solve any of our packing problems with this. But it turns out you can be clever to shrink the problem instances so that you can actually get something productive from cylindrical algebraic decomposition. So in the real case, you can pass to a combinatorial structure of the Gram matrices. Maybe you say that given a system of lines, you pass to the Gram matrix and you ask which off-diagonal entries achieve equality in the coherence. You make the graph corresponding to those adjacencies, and you get what's called the contact graph. It turns out you can show that an optimal packing has a particular type of contact graph. It's something that we call D-secure. This is a combinatorial property on the graph. What that means is you can scroll through all possible graphs that satisfy this property, and now you're identifying a subset of all possible Gram matrices that you need to consider in order to find an optimal packing. If you want to get the most out of this theory, you look for when n is small relative to d. That's when you get the most edges in your contact graph. And we actually know the optimal packings when n equals d plus 1. So let's think about n equals d plus 2. In this case, the d-secure graphs take one of two forms. They look like this. And so for each form, you can scroll through all possible sign patterns of the coherence entries and perform a CAD query to see what the optimal coherences look like. And when you do that, you end up with this characterization of optimality. There's a putatively optimal packing of 6 lines in R4 given by Neil Sloan, and we were able to prove that his packing was in fact optimal using this method. This method's too slow for the next case where n equals d plus 2, but you can speed up CAD further. So again, you're scrolling through contact graphs, but instead of running CAD on all of the cases, maybe you roll out the suboptimal cases using a different method. Let's call that X, and then exactly optimize the optimal case using CAD. You can take X to actually be CAD with just a clever implementation of CAD and figure out the 7 lines in R5 case. In order to tackle 8 lines in R6, you need to be more clever. We developed a numerically robust version of Stengel's positive Stellensatz. This positive Stellensatz is a way of establishing that sets like this are empty. So how do you know that there are no real numbers x for which x squared plus 2x plus 2 equals 0? Well, if you remove 1 from this, you end up with a perfect square, and it somehow needs to equal -1. And that's impossible because perfect squares are non-negative. This completing the square trick will always work to show that a semi-algebraic set is empty, it turns out. If it's empty, then there exists a certificate of this form. This is the content of Stengel's positive Stellensatz. So that open problem I showed you earlier with 8 lines in R3, it turns out that the same technique identifies the solution, but in this case, you have to use spherical geometry and interval arithmetic and some linear programming. And that's the story there. You have a bunch of ways of getting lower bounds from numerical real algebraic geometry. And you might wonder, how do I get upper bounds? How do I find new constructions? And this is the approach of non-convex optimization that I told you is particularly frustrating. Neil Sloan provides putatively optimal packings in the real case, but in the complex case, Neil Sloan does not provide a table. And this is actually a good opportunity for students. If you have students that are interested in doing some sort of optimization, then you should throw them this problem. And in fact, they can compare their results with a table that we've developed. These are the putatively optimal complex projective packings. This gives a leaderboard for everything that we know so far. And if your student or if you come up with a packing that beats what we currently have in the leaderboard, you can email it to us and we'll add your initials to the leaderboard. So you get some street cred that way. There's also money. My colleague John Jasper will give you $100 if you find a new complex ETF with in dimension at most 7 that we don't currently know to exist. And Emily King will give you a cup of coffee. In fact, she'll give you really fancy coffee if you prove that the columns of this matrix form the optimal packing of 5 points in CP2. So that concludes the second part of my talk, and I'm looking at my clock, and it appears as though I don't have time to go into the third part. Is that correct, Gary?
Unfortunately, yes. It seems that maybe we can say an extra 10 minutes if there's a sped up version is possible.
How about I give this to you in 3 minutes?
Okay, then that's totally fine.
Great. I'm going to give you 3 minutes of part 3. So Zauner's conjecture is on the edge between where the Welch bound is optimal and where it's no longer optimal. So this is where I have complex space, d dimensions, and I have d squared vectors. So it is conjectured that there are always d squared vectors in d-dimensional space that form an equiangular tight frame. This is the content of Zauner's conjecture. This is the biggest open problem in this area. They're known in quantum information theory as SICs, SIC, and they have important applications over there. The way people construct these things is by using the representation theory of the Heisenberg-Weil group. In particular, they used what's called the Schrödinger representation. So all translates and modulates of a given seed vector. If your seed vector is called phi, it turns out that you're going to be an ETF after spinning up with the Schrödinger representation precisely when you minimize this potential. This is a function of phi. It's known that this is greater than or equal to this particular number, and you achieve equality precisely when you spin up a seek. So people have numerically optimized this potential, and it's highly non-convex, so lots of local minimizers. But regardless, we found, the community has found numerical solutions for D all the way up through 151. So everyone believes that Zauner's conjecture is true. No one has a proof. In order to inch towards a proof, folks have tried to get algebraic expressions for these seed vectors. So what does it take to actually achieve equality in that potential lower bound? People have thrown Grosvenor bases at this, and they found real solutions in small cases. Grosvenor bases take a long time to solve for, but when the dimensions are small enough, you can trick it into giving you something. And for all of the algebraic solutions we have to date, they all satisfy this feature. The outer product of the seed vector times its conjugate transpose, the entries of that always live in a abelian extension of this real quadratic field. Okay, in this particular one, Q adjoins square root d minus 3, d plus 1. You can use this number theoretic feature of these seed vectors in order to promote numerical solutions to true solutions. Think of taking a numerical solution, grabbing thousands of digits of precision, and then somehow rounding to the nearest member of this number field. This has considerably extended the range of the solutions that we have available. Blue is what Grosvenor bases gave us. Red is what this numerical to exact routine has given us. But there's still an issue of the description length is too long. If you take the size of the file used to describe these seed vectors, like SQRT, open parentheses, 2, etc., you count the number of keystrokes it takes to describe these things. That gives you the vertical axis here. The horizontal axis is the dimension of the seek. So it's growing like d to the 4. That's what this dotted line suggests. And you should hope for a shorter description of these things. It turns out that there is a correct expression conjecturally going through the Stark conjectures. So Stark has these conjectures about certain units generating certain number fields, and it appears as though the Stark units provide an explicit description of these seed vectors. This follows from a strengthened version of Stark's conjecture, and it's been used to come up with new explicit examples of seeks. We don't have, GeneCop is still working on extending this to all dimensions, so, but I expect it to be publicized in the next couple of months, something in this line. So look out on the archive for an update here. This is the hope that we have for an explicit solution to Zauner's conjecture, but it seems to factor through the Stark conjectures. So we'll probably end up with a conditional theorem in this direction. In order to get an honest theorem, you might try to go implicit instead of explicit. So maybe using some sort of fixed point theorem. This is something Peter Shore asked about on Math Overflow. I have an idea on how to relax the search to biangular frames instead of equiangular type frames. It turns out that in certain cases, you can show the existence of an ETF using the intermediate value theorem. Anyways, I've talked about a bunch of different problems, lots of open problems in this world. I'm pretty excited by it, and I hope you are too. And that concludes my talk. So I'll entertain your questions now.
Thanks a lot for your really nice talk. So I'll stop recording now, and you can start to ask some questions.